charge, mass, and indivisible, alas. Those were some ingredients chosen to create the electron particle. But an extra ingredient was added to the concoction. Spin.
Let me ask you this. Are electrons spinning? Actually, both can be right. Let's see why. No, because the surface of the electron would have to be spinning faster than the speed of light to exhibit this rotational motion, assuming if electrons have surfaces, which we know they don't. The only possible explanation for this is that it's built-in or intrinsic, and cannot be described classically. So they're not spinning like the spinning ball we know, but we still call it spin. Now you might be wondering, how do we even know that this property exists? Well, if electrons truly exhibit this property, they would have a magnetic field. Thus, it can be affected by another magnetic force from the outside. Let's see if this is the case in a 1922 experiment, where a beam of silver atoms representing electrons were shot through a special magnetic field. Will the atoms end up in a random distribution, or in some other way? Turns out, the atoms split into two distinct groups, indicating the possible orientations of its magnetic moment. Spin was therefore quantized. +1/2 and -1/2. But that's only for the electrons. What about the other particles? A particle can have an integer spin, which we call bosons, or a fractional spin, which we call fermions. This difference also affects their atoms. Let's assume that each bowl is a different energy state. Bosons, unlike fermions, can be stacked in one bowl, but fermions, specifically electrons in multi-electron atoms, require a different set of quantum numbers from each other, as per the Pauli exclusion principle. If not, all atoms would be in the lowest energy level and the minimum possible size. Like chemical X to Powerpuff Girls, spin to electrons literally saves us from destruction, enabling matter and our universe to exist.